Right, let's do some physics. This is the June 2020 paper. It was for 1 hour and 10 minutes, the combined science, worth 60 marks, so that's basically 1 mark per minute. And it's the paper 6, which means it's physics paper 2. And it's higher tier. If you're not sitting the Edexcel paper, just make sure you do paper 1 as well as paper 2, and then that'll cover all the syllabus for something like Aqua, as all the syllabuses are very similar. Question 1a. Figure 1 shows a small piece of copper about 3 centimetres high. A student wants to determine the density of copper. The student uses a balance to measure the mass of the piece of copper. Explain how the student could measure the volume of the piece of copper. Right, well, you're going to need one of these displacement canisters, otherwise known as a Eureka can. So fill it up to water, up to there. And you want to put a measuring cylinder here, empty. And when you basically pop the piece of copper in, that water level is going to rise, and we'll just catch the water in there. And 1 milliliter of volume of liquid equals 1 centimeters cubed of volume. They're otherwise known as a Eureka can. So place the piece of copper in the can, and the volume of water displaced equals the volume of the copper. Part 2. The mass of the piece of copper is 0.058 kilograms. So that's the mass. The volume of the piece of copper is that, so that's our volume. Calculate the density of copper. So that's our question mark. So density equals mass over volume. If you didn't know that, just look at the units. Just literally take how many kilograms it is and divide it by how many meters cubed it is. That's in kilograms, that's in meters cubed. So just 0.058 kilograms divided by 6.5 times 10 to the minus 6 meters cubed. And that equals 8,923. Part B. A student wants to determine the specific heat capacity of copper. Figure 2 shows a piece of copper with a thread tied around it in a glass beaker of boiling water. The student leaves the piece of copper in the boiling water so that the copper reaches a temperature of 100 degrees C. The student uses the thread to take the piece of copper out of the boiling water. Right, that's the final temperature, just in case we need it in a second. The student puts the hot piece of copper into a different beaker of cold water at 20 degrees C. The apparatus is shown in figure 3. The student assumes that the thermal energy gained by the water equals the thermal energy lost by the piece of copper. Right, so basically that piece of copper was 100 and it's going to cool down, and that water was 20 degrees C and it's going to heat up. So the final temperature is going to be somewhere in between those two temperatures. The water and the copper both reach a temperature of 22, so there you go. So the copper cools right down to 22 and the water heats up a little bit to 20. The cold water gains that much energy. The mass of the piece of copper is that. Calculate a value for the specific heat capacity of copper using these results. Use the equation. Right, change in thermal energy equals mass times by specific heat capacity times by change in temperature. So this E here, on Aqua they use E, but in Edexcel they use Q. And it's the change in, so we'll put this little triangle on the front. Right, we just need to rearrange this then. So C is going to equal delta Q divided by M times by delta theta, which is the change in the temperature. Let's pop the numbers in. The change in temperature, well, the copper went from 100 down to 22, so that's 78. And notice that it's the capacity, the heat capacity of the copper that they're after. So we needed the mass of the copper and the change of temperature of the copper. And that equals 232.1. I'm just double checking that the units are good. Part 2. The value for the specific heat capacity of copper obtained from the student's results is lower than the correct value. State 2 ways that the experiment could be improved to give a value that is closer to the correct value. Right. If we look at the equation, the reason why this number here is less than it should be is maybe because this value here was less, or the values on the bottom should be more. So let's look at the picture. Right, well, we could improve our energy reading by putting some insulation around the outside. And we can improve our temperature reading by having a stirrer in the water to make sure that the thermometer is not sitting in like a hot pocket or a cold pocket. Right, so what I've put in the brackets, you actually wouldn't need to put that down for the examiner. I've put it down just so you understand why I've said those two things. I mean, you can write them in the exam, it's up to you. Question 2. Figure 4 shows a drone. The drone has 4 spinning blades. The upward force produced enables the drone to rise in the air. The speed at which the blades spin is measured in turns per minute. Figure 5 shows how the upward force produced by the 4 blades depends on the speed at which the blades spin. Right, so that's the upward force there on the y-axis, and that's the speed in turns per minute on the x-axis. Describe the relationship between upward force and speed shown by the graph. Right, it's worth 2 marks. Well, the first thing you notice is that as the speed of the blades increase, the force is getting bigger. But it's not a straight line, so we see it's non-linear. And what you'll notice is I try to use their words. They've said upward force, so I've said upward force. And they've said speed, so I've said speed. If it was a straight line, we'd say linear. That's how I've trained my students. Part B. A different drone has a mass of 4.5 kilograms, so that's our mass. The drone rises from the ground to a height of 20 meters, so that's height. Calculate the change in gravitational potential energy, so GPE is question mark. when the drone rises through a height of 20 metres. The gravitational field strength, so G is 10. Right, so you're supposed to know that GPE equals mass times by gravity times by height. Pop the numbers in. So the mass was 4.5 kilograms. Gravity on Earth is 10 newtons for every kilogram. And the height was 20 metres. And that equals 900 joules. Part 2. State the amount of useful work done by the blades as the drone rises through 20 metres. So the useful work done, that's going to be the same as the energy transferred. So we've just transferred 900 joules of energy to the drone, so that means we've done 900 joules of work. Part 3. It takes 4 seconds for the drone to rise through 20 metres. Calculate the useful power developed by the blades in this time of 4 seconds. So it's given us time, we need power. Right, well, power equals work done or energy transferred divided by the time taken. So that'll be 900 joules divided by 4 seconds. And that comes out as 225. And that's watts. Remember, 1 watt equals 1 joule per second. So that's why we take the joules and divide it by the seconds. Question 3. Figure 6 shows the magnetic field of a magnet. At which point is the magnetic field the strongest? Well, it's the strongest where the lines are the closest together. So that's going to be B. And just to be sure, it's always the strongest nearest the poles, just in case you didn't know that. Part B. Figure 7 shows a wire carrying a current. Draw on the card in figure 7 the magnetic field that is produced by the current. Right, you need to use the right hand grip rule. Now if you were, I'm laughing because I'm going to try to draw a hand here. If you were to draw your thumb pointing the same direction as the current, and then your sort of knuckles would go over that way, wouldn't it? And then your fingers would come round here, like that. So these fingers here, they represent the direction of the magnetic field. And as I say to my students, the field goes from the knuckles, knuckles is north, fingertips is south. So basically the magnetic field's going to be going clockwise as you're looking down on top of it. Now it's worth 2 marks, so better draw the full thing, to be honest. Right, it would actually be getting further apart as it's going further away. Make sure that you've got your arrows on. So put more than one line on and make sure you've got your arrows pointing which way it's going, and that's how you'll get your 2 marks. Question C. Figure 8 shows 2 metal rods carrying a current. A metal roller touches both rods and completes the circuit. The roller is in the magnetic field produced by a magnet. Right. The magnetic flux density of the magnetic field of the roller is 1.2 Tesla. So that's B. The current in the roller is 2.5 amps, so that's I. The length of the roller carrying the current is 0.06 meters, so that's L. Calculate the force on the roller. Right, you just basically need to bang the numbers in. So 1.2 Teslas times by 2.5 amps times by 0.06 meters. And that equals 0.18 newtons. Part 2. Describe how Fleming's left-hand rule can be used to determine the direction of the force acting on the roller. You may draw a diagram to help your answer. Right, so Fleming's left-hand rule. Again, this picture is going to be rubbish. Right, there's your wrist. There's your sort of thumb going up. Then your first finger comes out, and then your second finger comes out there. And then you've got a sort of couple of little fingers tucked down there, haven't you? Right, the thumb represents the movement, or some people like to say the thumb instead of thumb represents the force. Right, same thing, it's the force that creates the movement. Right, your first finger shows you the magnetic field, and your second finger shows you the direction of the current. Now remember, the current goes from positive to negative. Alright, it's conventional current, not actual electron flow. And remember, your magnetic field always goes from the north to the south. So, as I say to my students, knuckles are north, fingertips are south. And they're all at 90 degrees to each other. A simplified version of drawing it would be like that. That's at 90 degrees to that. That's at 90 degrees to that. And that's at 90 degrees to that. And you'll actually get all 3 marks for drawing that picture and putting the labels on like I have done there. Part 3. Draw an arrow on figure 8 to show the direction of the force acting on the roller. Right, we're going to have to go back and look at the picture. So if we use the rules that I've just described here, right, so the current's going to come in this way, which means it's going to come out that way. So the current's going to come along here. It's going to come along this rod here. Now, your current then is going to go through this roller that way. So that's going to be your current. The magnetic field, if I do that in blue, is going to go from north to south upwards. So that's the mag field. Right, if you take your left hand and your first finger is going to be the field, so that needs to point upwards. Your second finger needs to be the current, so that's sort of pointing in towards the page. Right, that means that your thumb is going to end up pointing that way, going from left to right. So that's the force. So that's the way that the roller is going to move. That's going to be the force on the ruler. So what you might want to do is you might want to just draw that green arrow in your actual exam. I've done the whole thing there just to try to make it easy for you to understand what I'm talking about. So that was going from left to right. But I've already drew it on the diagram above. Right, question 4. Figure 9 shows a spring standing on a table. Weights are added to the spring as shown in figures 9b and c. Estimate the original length of the spring as shown in figure 9. Right, well, the original length is just the length that it is before you put any compression onto it. So if we just go across there, what's that, about sort of 52 millimeters? That's in millimeters, and they wanted it in millimeters, so just checking they weren't being funny. Right, part 2. Describe how the reduction in the length of the spring when weights are added can be determined. Right, okay. So when we've added the weights here, the original length was 52, and now it's gone down to 40. So if we take the original length, 52, and take away the length now, 40, that'll tell us how much it has compressed. So we just need to write that as an equation. So reduction in length equals original length, take away the new length. Part 3. State 2 ways that the experimental procedure could be improved. Right, well, what I noticed when I was drawing this is that spring is quite far away from the ruler, so if we bring that spring a little bit closer to the ruler, that'll definitely make it easier. And maybe if we could put some kind of pointer on the spring, so it points straight across, that would be another way. Or we could always go for our trusty take repeats and create averages. Yeah, and I mean, look at the ruler. It hasn't even got like 1 millimeter divisions on, so use a ruler that's more accurate. I mean, you could say add more weights to increase the range if you wanted. And also, go down to eye level so there's no parallax error. If you don't understand what that means, don't worry about it. There's loads of results there. It's only worth 2 and I've put like 5 different things. Part 4. Give one reason why the reduction in length eventually reaches a limit as more weights are added. Right, let's have a look at the picture. Right, it's going to reach a limit because at some point that spring's going to get so compressed that the spring coils are touching each other. And again, that could be worth 2, just in case they make it worth 2 this year. Part B. A different spring is extended. A force of 0.5 newtons, so that's our F, gives an extension of 13 millimeters. That's X, right. As soon as I've saw millimeters there, I'm just going to check. They want it in newtons per meter. So I'm going to convert that into meters by dividing by 1,000. Or in other words, sticking a times 10 to the minus 3 on the end. Calculate the spring constant K in newtons per meter. Right, so F equals Kx. So therefore K equals F over X. We'll just pop the numbers in. So it's 0.50 newtons over the top of 13 times 10 to the minus 3 meters, and that equals 38.46. I mean, they've put that number there to 2 decimal places, so that's why I'm putting mine to 2 decimal places as well. Part C. Another spring is extended. The work done to extend the spring is 0.14 joules, so that's work done, or energy. The spring constant of the spring is 175 newtons per meter, so that's K. Calculate the extension of the spring. So the extension is our question mark. That's what we're trying to find. Use an equation, select from the list of equations at the end of the paper. Right, so we've got E, K and X, and we're trying to find an equation with those things in. Right, well, as you scan down, there we go there. E, K and X. So E equals a half KX squared. A equals a half times by K times by X squared. Now we're going to need to rearrange that. So therefore E divided by a half times by K will give us X squared. We don't want X squared, we want X. So therefore if we square root both sides, that will get rid of X squared and just leave X. Right, let's pop the numbers in. So that's 0.14 joules divided by a half times by 175 newtons per meter. Square root the whole lot. And that equals 0.04. And that's going to be meters, because that was in meters there. Question 5. A student investigates resistors connected in parallel using a number of resistors. Each resistor has the same resistance. Figure 10 shows a circuit diagram with one resistor R. Add to figure 10 a voltmeter to find the potential difference across resistor R. Okie dokie. So we just need to pop that voltmeter in there. And another resistor in parallel with R. Right, another resistor in parallel with R would just be that. Now if you're thinking, will that affect this voltage here? The answer is no, because remember, if you've got components in parallel, they each get the same amount of voltage. Part 2. State the measurements that the students must take to find the overall resistance of the resistors in parallel. Right, so to get the resistance of something, you're going to need to measure the voltage and divide it by the current. So measure voltage and measure the current. You could say across R, and you could say through R. You don't need that though. Part 3. The student investigates how the overall resistance of the circuit changes when additional resistors are added in parallel to R. Each resistor once again, has the same resistance. Figure 11 shows the results of the student's investigation. State the resistance of a single resistor. Right. What we got? So across the bottom it says the number of resistors. So if we go here, that's one resistor, and it's got a resistance of 1 ohm. So 1 ohm. One resistor, 1 ohm. Right, part 4. Comment on the relationship between the overall resistance of the circuit and the number of resistors in parallel. So number of resistors in parallel overall. 3 marks. Use information from figure 11 to support your answer. Right, that's why they're giving you 3 marks, because you need to put some information in. So what can we see? Generally, as the number of resistors increase, the overall resistance decreases, and it's a curve, so it's non-linear. So do you know before how I said to use what they've said? So number of resistors, overall resistance. And because it's a curve, it's non-linear. Remember, that's the way I want you to answer it. If it was a straight line, say linear. And that's 2 marks, but we've got 3, so we just need to back it up with some data. So, for example, when two resistors, so 2 resistors, the resistance is 0.5 ohms. And when we've got, I'll say 5 resistors, that's easy. When we've got 5 resistors, the overall resistance is 0.2. So that's a nice easy thing to read off the graph. Okay, so that just backs up there what I'd said before. As the number of resistors increase, the overall resistance decreases. Part B. A different circuit is then set up with 2 resistors as shown in figure 12. Right, so they're in series now. Calculate the potential difference, so the voltage across the 15 ohm resistor. So V equals I times by R. We just want that of the 15, so we just need to know how much current is going through the 15 ohm. And what is the resistance of the 15 ohm? That's just 15 then, isn't it? And that equals 3 volts. Part 2. Calculate the total power dissipated when there is a current of 0.2 amps in the 2 resistors. Use the equation P equals I squared times by R. Now they're wanting the total power this time, not just the power of one resistor. So instead of just using resistances like 15 like we did last time, we're going to have the total resistance. Okay, to get the total power, you're going to need to use the total resistance. So pop the current in, 0.2, remember to square it because it's I squared times by R. So that's 15 plus 20, 0.2 squared times by 35. Remember to do the 0.2 squared first, then multiply it by 35. Don't square the whole lot, and that comes out as 1.4 watts. Question 6. The magnitude and direction of a force can be represented by a vector. Figure 13 shows the forces acting on 4 identical trolleys. The arrows show the magnitude and direction of the forces. Remember, a vector is just something that's got size and direction, such as an arrow. Which diagram shows a pair of forces that will produce 0 acceleration? Right, so basically the two forces, if they were pushing a car, need to cancel each other out. So that's going to be B. A will make the trolley accelerate. C would make it sort of accelerate that way. And D is going to make it accelerate a little bit this way. So we need these arrows that are equal in size but opposite in direction. So they'll cancel out and create 0 acceleration. Part B. Figure 14 shows 2 small boats pulling a much larger ship. The ship is connected to the boats with ropes. The tension T in each of the ropes has a magnitude of 20 kilonewtons. The ropes are at right angles to each other, right, as we can see here in the picture. Draw a vector diagram and use it to determine the resultant force that the boats exert on the ship. This is why you need to take a ruler into the exam with you. Right, you'd basically draw a line going down that way, and you draw a line going that way. And then, if you did tip to tail, so if we imagine, if we took that and popped it there, and then if we took this and popped it there, what you're after, from there to there, that's your resultant. And you'd measure that. Now you'd have to do it by a scale drawing, really. So what if you did 1 centimetre equals 10 kilonewtons? You draw your little line across there, 2 centimetres long. Draw your little line down there, 2 centimetres long. And then when you actually measured this here, however long it is, that would give you the correct reading. Now, if that's 2 centimetres and that's 2 centimetres, this here would actually be 2.8 centimetres. Now, some people prefer to do this by Pythagoras, because what you've noticed is you've actually created a right angle triangle where both of the sides are 2 centimetres. So if you did 2 squared plus 2 squared and square rooted it, that would equal what this is, and it comes out as 2.8. So that would be 2.8 centimetres, and then 1 centimetre equals 10 kilonewtons. So therefore 2.8 centimetres would be 28 kilonewtons. And that's your answer. So if you're not too sure about using Pythagoras' theorem, just make sure you take a ruler in and do a scale drawing. And finally, last question. Part C. Figure 15 shows a wooden block connected to a weight by a string. The string goes over a pulley. The surfaces of the table and the wooden block are both rough. The wooden block moves across the table at a constant horizontal velocity. Several vertical and horizontal forces act on the wooden block as it moves. Explain how the forces keep the wooden block moving across the table at a constant horizontal velocity. Your answer should refer to all forces acting on the wooden block. You may add to the diagram to help with your answer. Right, what you've basically got is weight pushing downwards. So that would be one of the vertical forces. You've got what's called a normal reaction force, pushing upwards. Remember, for every force there's an equal and opposite force. Then you've got the force of the string pulling it forwards. So that's created by tension in the string. And then you've also got friction, which opposes motion, going backwards. So if we just talk about those four forces, then there's 4 marks, and we know that it's a constant horizontal velocity, so we'll just have to say that the overall resultant is 0, so that must mean that the normal force upwards equals the weight down, and the friction force to the left must equal tension to the right. So probably easier than what you think. They have actually made it sound really complicated. So if block is moving at a constant speed or constant velocity, all forces must be balanced. Just going to rub that little block off there. Because you won't, that's just 1 mark there. So we'll say tension forward or to the right is going to equal friction to the left. We'll just say that friction opposes motion. Just our standard definition of what friction's actually doing there. And they're the horizontal forces. And then the vertical forces. Got the weight down. Must equal the normal reaction up. Right, we'll say that the tension comes from the string. I'll be honest, I think I can get 6 marks out of that already. I think I've been a bit harsh with myself, but just in case, I'll just say there's no vertical movement, because those forces, those vertical forces, are balanced. And there we go. So I hope that's been helpful. I know I've been over loads of past papers with my students, and their grades are all improving. Going over past papers is the best type of revision that you can do, and the more you practice, you will increase your success. Right, work hard, be nice, see you in the next video. Bye for now.